Well, today's session is a fireside chat on the topic of latest AI developments. AI, as you know, artificial intelligence is a rapidly changing, and as it changes our world too. And AI chat robots are one of the most visible examples of this change. And most of us have probably interacted with an AI chat robot already. We may have used one to create a trip plan or organize a document or even just chat for fun. And AI chat robots are used in a variety of settings. Their capabilities are constantly expanding. While they offer many benefits, there are also potential dangers associated with AI chatbots. For example, AI chat robots could be used to spread misinformation or propaganda, or to collect personal data from users without their consent. So it is very important to be aware of the potential dangers and use them responsibly. IT Society is proud to host the Fireside Chat with Talip Ozturk as he interviews Amin Ahmad, who is a leading expert on AI. Before moving on to the discussions, let me also introduce our speaker and the interviewer briefly. Today, our guest speaker is Amin Ahmad. He is a co-founder and CTO of Vectera, which provides a complete ML search pipeline, from extraction and indexing to retrieval, re-ranking, and calibration. They also provide neural search, marketing, and conversational AI solutions. Prior to Vectera, Amin served as a senior engineer at Google Research for 10 years. Amin led the development of question answering and neural information retrieval systems that have been launched into several Google products. His 20 years of search industry experience include working with Fortune 500 companies, startups, and state and federal governments. Amin holds a BS in computer science and mathematics from Bowling Green State University. And today our interviewer is Talip Ozturk. He is the head of engineering at Vectera. Before joining Vectera, Talip was an engineering manager at Google, where he led the scalability of AlloyDB, a relational cloud database service. Talip was the founder and CTO of Hazelcast, an in-memory database company that was used by all major banks in the US and Europe to build distributed and scalable applications. He has over 20 years of experience in software development after he self-learned how to code. Talip holds a BA in International Business from Johnson & Wales University. So we know the guest speaker and the interviewer, and we are ready to move on to the fireside chat. Our session today will be in two parts and will take about 1 hour. In the first part, Amin will give a brief introduction on the topic, and there will be a discussion with Talip and Amin. And in the second part, we will open up the floor to questions from the audience. So the link for the Slido is shared on the chat, should be shared on the chat. Please add your questions and upvote the questions.
All right.
That's it. All I have to say. Thank you. And Talip, you can take over.
All right, awesome. Thanks so much for having us. It's so much fun. We'll learn we'll discuss some of the exciting developments. But I want this to be also a little bit of learning, so it's not like all fancy stuff about AI. So we'll dig into the basics of AI a little bit. Please use the I think, what's the name of the app Slido for your questions. I'll be watching those questions also. So I mean, so what was your journey so far? Like, how did you end up at Vectera? How did you get involved with AI?
Yeah, so it's a pleasure to be here and talking to all of you. I got into AI research at Google around 2012. I came into a research group led by Ray Kurzweil. For those of you who know, he's basically a well-known inventor in computers. He created one of the first ASR companies, Kurzweil Systems, back in the late 1980s. So he came to Google with the mission of investigating artificial intelligence from the perspective of language understanding. Somehow he had this insight in 2012 that the next leap in artificial intelligence would come from this area and from getting computers to understand human language more like the way we understand our own language. So I spent 8 years with him, initially as an engineer, but then went into the actual research myself. I left Google in 2020 to start Vectara, mainly because the breakthroughs in language understanding during this decade, the 2010s, were very, very large. And a lot of us in Google research felt that perhaps Google's management culture was such that they're very conservative, not open to taking risks, and not fully utilizing, I think, the potential of the technology that had been discovered there. And for instance, being very interested in applying that in certain directions like ad serving, but not having interest in other kinds of applications. So that's what's kind of led me to leave in 2020 and start Vectara.
So you're thinking that while like big companies like Google and Amazon, they can do crazy stuff, they can spend a lot of money on research, and they can build crazy AI solutions, you're thinking that you can do something similar with as a startup? Like, isn't that too much of a like
well, not every large company was as open or forward-looking as Google in their research program. I think Microsoft Research is another good example of that. But Google was, they were very idealistic in their research, and when they would do research into deep learning, first of all, they led the industry in this area in the 2010s. I mean, all of the major papers that came out were actually from Google, whether it was word vectors in 2013, transformers in 2017, or pre-trained models, BERT, in 2018. It's all coming out of Google. And Google had this culture of publishing and making the research open. So it attracted a lot of, I think, idealistic individuals who were really looking at, how can we get the maximum benefit to society from this kind of research? So as a result, it did become an issue then when that kind of research was being harnessed in very narrow ways, for instance, like ad serving and things like that. So what's happened, particularly with the release of foundational models beginning in 2018 with BERT, is that the paradigm for working in artificial intelligence has fundamentally shifted. So you take these models off the shelf and you're no longer training them from scratch. You're taking one of them and you're fine-tuning it. So combining that with the rapidly improving hardware for actually doing this training, like an A100 from NVIDIA is a massively powerful piece of hardware for training neural networks. You can have it for $12,000 now. 7 or 8 years ago, only Google and Microsoft had the budgets to afford to do large-scale machine learning. Now, much smaller companies can engage in it.
Is it the hardware the real deal here to making that change? Like now, like I remember, like with my from my friends, I was hearing about TensorFlow, AI, like back in 2000, even 15, 16, but I never got like really excited about any of that stuff. I remember like they laugh about things like, oh, even the biggest computers that Google has cannot even predict by looking at the image, they cannot predict what that is as good as like a 7-year-old kid. So it's like, it was super primitive. Like, and then most of the AI things that I heard was like, oh, this like a data engineering, like numbers and all that stuff, but never became a thing. When did it become a thing? Like, is there like a historical timeline that things radically changed other than the hardware?
Yeah, so the hardware improvements, the exponential improvements in hardware have been critical to this. If that hadn't happened, I don't think we would be at this position today with systems like ChatGPT, but that's not the only thing. So essentially, I can mark 3 key moments in the 2010s that were really watershed moments for the development of language understanding by computers. The first came in 2013 with the introduction of word vectors, where computers were able to learn the meanings of words it's the semantic meaning of words and how they related to each other in a completely unlabeled way, meaning without humans labeling examples. You just fed in a text corpus like Wikipedia, and on the other end, you got these, nicely trained representations of every word. And then in 2017 and 18 in particular, where you're constructing not just the meaning of words, but entire sentences and paragraphs in this unstructured manner. From the perspective of the software algorithms, these were some of the major breakthroughs that then led to the emergence of large language models that power ChatGPT and other systems today.
I remember a paper that everyone talks about this, what was the name of the thing? Attention is all you need.
Oh, yes.
Why is that so popular? What is it saying?
So attention is all you need is the paper in 2017.
I like the name, by the way. It was like a super catchy name. Attention is all you need.
Yeah. So it's the paper that introduced something called transformers,
okay,
which were initially introduced in Google research, I believe, for machine translation, for taking natural language from one language and translating to another, but have rapidly become, the basis for all kinds of breakthroughs in deep learning, not just in language, most prominently in language, but also now it's extending into fields like vision and video understanding, things like that. So the idea was that it was always challenging for feed-forward neural networks to process sequential information. And language is essentially, it's a one-dimensional sequence of words, but to understand the meaning of a word, you need to look at its context and potentially look pretty far away in the sequence to understand. So if you use a pronoun, for instance, like he, who is the he referring to? You might have to look back a sentence or two to understand that. So feed-forward neural networks, which are the kind of neural networks that you can really scale up to very large sizes and train efficiently, didn't have the ability to, pay attention to other words in the sequence.
Okay.
Recurrent neural networks did, but the problem with recurrent neural networks is they were much harder to train. You couldn't train the models as big, and then they were also difficult to productionize. So transformers, basically, it was describing a technique to give feed-forward neural networks that ability to pay attention to different things in a long sequence that recurrent neural networks had before.
Okay, so but if doing it efficiently.
But doing it much more efficiently and at much larger scales.
So he understands the context. He understands what is it that you're talking about?
Yes.
Okay, so I just when I read anything about a neural network, I keep seeing something like this. Let me share my screen and so you can walk me through that stuff. Like I see something like this. Like there's neurons or dots and it just multiple layers. Well, what is this? Like what is it? What's going on here?
Okay, so what you're actually seeing over here, okay, this is so in the upper left corner you're seeing a handwritten digit 2. Okay, and this is a very classic example where deep learning was applied successfully, was in recognizing handwritten digits. And in fact, one of the first users of machine learning was actually the US Postal Service for automatically recognizing handwritten zip codes. So what you have is the pixels, the actual pixel intensity values coming into that first layer on the left and being transformed by a very simple nonlinear function. Those are kind of the nodes or neurons of a neural network. Those are the circles in this diagram.
Circles, okay.
It's performing some kind of transformation, nonlinear transformation, and then that value that comes out is being broadcast to all of the nodes in the next layer, okay? And the key thing is that it's being broadcast on those edges, and those edges, although it's not visible here, have weights associated with them.
So the connection between each neuron here, between each layer, so there's a weight associated with those?
Exactly, and that's just it's a floating point value.
Okay.
And it's a multiplier. And what you see then happening in the next layer, okay, is, some of those neurons are lighting up. Those are the neurons that are producing the strongest output to send to the next layer. And as you're going from layer to layer, eventually in the final layer, what you see is actually the digits from 0 through 9, and it's performing a classification at that point and predicting which digit is written there in the upper left corner. So basically the brightest one that lights up in this case is the 2, is predicting a 2. So in the training process of the neural network, you actually feed a lot of these examples of the handwritten digit and what number it actually represents. And the neural network learns to adjust those weights.
Oh, okay.
Yeah.
So the layers are the same during the training and the runtime,
Correct.
but so something extra happens during the training.
Right.
So as you feed the training data through the layers,
Mhm.
so it eventually ends up at the last layer, and it will create a vector representing that input. And you probably have like a correct version of that vector. And then you just say, like, how far is that from the actual answer? So what do you do that? Like, what do you use to do? So now you know that the eventual vector that you end up with is not exactly the same as the actual thing that you know that it was representing. So, and there's like a distance between the two.
Exactly. So that's correct. So in this example here on the screen, what's being output are actually, the neural network is outputting the probabilities in this last layer. So the probability that it's a 2 versus a 1 versus a 0, and they all have to sum to 100%. Now, the loss function is responsible for computing how much penalty the neural network
What's
incurs.
the loss function? Is that the, like, how far is it from the actual answer?
Exactly. It's computing the distance between the actual answer and the answer output by the neural network. And then what the neural network is actually trying to do during training is to minimize that loss function over time as it trains. So initially, these weights are all uninitialized, and it's just going to basically output a random answer. But over time, it should get more and more accurate. So the neural network is trying to minimize that loss function. So at every step, it basically goes in and adjusts the weights a little bit to decrease the loss function.
Okay, so training means then you feed data from the first layer all the way up to the end, and then you look at how far you are from the answer, and then you go back to all these layers. So that's like a going backward.
Yeah, and that's
And
called
then
backpropagation.
Backpropagation.
Okay.
And then you adjust the weights so that the next time it will get closer to the answer.
Exactly. And you want to carry out this process gradually, not all at once in every step.
Why would you not do that like immediately?
Because what happens then is you end up with this kind of oscillating behavior that doesn't converge. So if you try to immediately update the weights so that 100% of the probability in this example goes to 2 and to none of the others, then it's actually it's not going to end up learning effectively in a generalizable manner. The next time you feed in the digit 3, you will get a wildly incorrect result. So you need to take small steps towards the correct solution, not jump at
Okay,
one step.
slowly you're learning
Yes.
to generalize things.
Yes.
So it's not even like in the database world that I feel more comfortable with. Things are very like black and white. Like it's very clear. Like
Yes.
if it is the number bigger than 5 or not. Like it's super clear.
Yeah.
But here things are more like it's pretty much like prediction. It's pretty much like fuzzy, and you're trying to generalize what it could be.
Exactly. Yeah, exactly. For those of you who are familiar with the idea of like finding like hill climbing or finding minima of functions, you need to take small steps. If you take large steps, you won't necessarily converge and ever find the minimum.
Okay, so then during the training, you pump a lot of data, eventually backpropagate and change the weights all the time. So these weights, and what is it representing? When I hear something like ChatGPT has 175 billion parameters, where is that number? Where is it in the picture?
Exactly. So if you look at the first 2 layers here, every neuron in the first layer is connected to every neuron in the second layer. So if you have M neurons in the first layer and N in the second, you can actually model these interconnections as an M by N matrix. And M times N is the number of weights, the number of connections. So when people talk about neural networks, they often use the term parameter. So these are kind of interchangeable. The parameters in the neural network is basically the count of the number of these edges.
Okay, so then there's so there are so many of them here,
Yeah.
and many of them in each layer.
Yes.
So just add them together, that's your number of parameters?
Exactly. So
Okay.
when they say ChatGPT is 175 billion parameters, it means that's how
That many connections.
Yes.
That's crazy.
Yes.
Okay. So, that means like all this training data just to figure out what these weights should be, all these
Exactly.
connections should be.
Yes.
So once you learn, like as you train, you learn what these weights should be, and eventually, when do you decide that you learned enough?
So that's a very good question. There's actually a lot of research into this, but in general, the way you do it classically is you hold out some data, and hold out means that you don't train on that data. So you're training on your main data set and periodically evaluating the performance of the neural network on the holdout set. Okay, and ideally, as the loss drops while you train on the training set, the performance on the holdout set continuously goes up. But at some point, that will cease to be true, and at that point, what we say is that, it's starting to overfit on the training set, and that's where you want to stop.
Okay, let me get the first part correct first, and then it will. Okay, so we're pumping a lot of data, and then eventually changing all these weights, and then so while we're doing that, we already know how far each trained data is from the actual answer. So that's the loss, and then we backpropagate and adjust the weights and all that stuff.
Yeah.
So as we keep pushing more data into the model, we already know if you are going, like if the loss is getting smaller or not. So we already know that.
Yes.
So we're hoping that the loss will be smaller as we go.
Yes. That will
And then
happen.
in the meantime, we're just going to be testing whether this is actually a good model or not with a evaluation data set,
Exactly.
which is completely different than the training data set.
So you want to look at the loss on the eval set.
Okay, loss should go down, and my evaluation should result in better results, accurate results.
Yes.
So and then if this is the case, then we know that we are on the right track.
Yes.
So is it gonna stop anywhere? This will we keep
well, usually one of two things happens when you're training with smaller data sets. What will happen is eventually the loss on the evaluation set, instead of going down, will start to head back up. If you're training on very, very large data sets, which is commonplace these days, especially with training large language models, where you're training, for instance, on all the text of the internet, then you won't really ever see the loss on the eval set go down, but it'll be an asymptotic curve. So there'll be a point of diminishing returns.
Okay, it will plateau somewhere, and then it won't grow as it won't get any better.
That's correct.
So then you know like, okay, so it looks like we come to the best performance we can get. Let's stop the training. Stopping the training means then what? Like you're no longer learning. That means your weights are not changing.
Right. At that point, they're frozen. So you freeze them.
You freeze them.
Yeah.
So then whatever, but all these weights between these layers are frozen, and then you just take it to the production and then run it.
Exactly. One way to think about it is, now the neural network, although it doesn't look like this, it's a very large continuous function. So you've learned the function, you've frozen it, and now you can apply that function in your production environment. Yeah.
So then you just ask something, and it will give you something back.
Exactly.
So what's special about, like, is there like a magical function or magical number of layers? So like, what is there, like a how do we define all that stuff, or is it more or less they're well defined, all these functions and stuff?
No, so I'd say this is actually what a lot of deep learning research is about, is understanding the effect of, let's say, deeper layers versus wider layers, and the trade-offs, different types of activation functions inside the neurons. All of this has been very intensely studied over the past decade. But one of the key findings, especially in the last 4 or 5 years related to large language models, is this concept of emergent behavior. So you can take exactly the same training regime, the same loss functions, and if you train, and the same training data for that matter, and if you train a neural network with 1 billion parameters, you're going to see a certain type of behavior. But just changing 1 billion parameters to 10 billion parameters, you may see entirely new behaviors emerge in the neural network. And it's actually very hard to predict. And unfortunately, I don't have the example here with me right now, but there were a few examples in the case of ChatGPT where it was discovered to have certain behaviors months after its release. So it means even the authors of that neural network don't know in advance what it's going to be able to do.
That's weird. So like in a database world, for example, if I built a database, I know exactly which functions the database will support.
Yes.
And the rest is like unsupported and it will never happen. I know for sure how it's going to behave. So now you're saying that like you don't even know how the eventual thing will act like.
Exactly.
So it can behave, it can have capabilities that you had no idea about.
Exactly. And this is actually the key to understanding why there's this nonstop race among companies to release bigger and bigger models.
So then what's like, so you're saying that these are all, I mean, it's still the good enough understood things like the layers and functions and then I'm assuming that data sets are also like available. Like, is it publicly available? Can I download the data set?
Yes, the data sets for actually training the base model, what's called the foundational model, is actually, it's the text of the internet. And, you know, in the last few years, the research community has, you know, made that available in a cleaned up form.
Okay, so there's a cleaned up form of data set that everyone can use. So then the models are also pretty much like the transformers, the architecture is also well known.
Yes.
Like the functions are pretty much known. Like, why don't I just create a much I don't know 100 layer, like I don't know 1 trillion parameter thing, and just pipe all this known data set that I can also already download. Like, what's wrong with that?
Well, although the hardware is rapidly getting bigger, when you're talking about the scale of hundreds of billions of parameters, these models are still very expensive to train from scratch. Even today, you know, you would be looking at a bill in the low single-digit millions of dollars for training one of these. So that's not within the reach of let's say a startup. But at the same time, that's really not necessary. That's not how you do modern NLP with deep neural networks. You actually begin with one of these base models. For instance, BERT is very popular. There's new models, foundational models that have been released in the past few months. In fact, last week, for instance, Stability AI released a large language model. You begin with one of those, and then you do what's known as fine tuning, where you take a relatively small amount of data and you adapt it to a specific task.
Okay, so just start from a model that's already been trained, and then put things on top.
And you can do that for a few $1,000s.
Yeah,
and that's kind of what's led to this explosion of startups in this space and the rapid progress.
It's more doable or like achievable than before. So,
definitely. Yeah.
So the cost will go down. So by the way, just like can I, as a developer, can I download a model, like let's say a DALL-E-like model, and just download and run on my laptop?
Yes. So actually, Stable Diffusion first came into the press for releasing under, I think, an MIT license, a competitor to DALL-E that was small enough to run on a consumer-grade GPU. It's called Stable Diffusion last year. So yes, these models exist. Hugging Face is basically a well-known clearinghouse for these models, so you can download most of them from there.
Okay, repository for all of them is there. Like just
Hugging
go
Face.
there, find a model that you like, download it, and start running on your laptop, basically.
Yeah, like some of them are laptop size, some of them might need, you know, bigger GPUs.
But yeah, it doesn't have to perform crazy.
Yeah.
But so when we talk about like billions of parameter models, what's the impact of that? Like other than the cost to train. So let's say we have it, and it's already trained. The weights are all set, frozen. I want to run it. So the more parameter means what? More accuracy?
Generally, yes, because what it's able to do is to create a finer and finer grained representation of its knowledge. So when you're training on the neural network and it's learning to do a task, like where is that knowledge being stored in the neural network? It's actually being stored in those weights. So those floating point numbers are somehow encoding that knowledge.
Okay, and what else does it cause? Like if I have more number of parameters, is it gonna run faster or slower?
It would generally run slower.
More means slower. Okay.
More means slower. There's more computation
More
happening.
computation happening.
Yeah.
Okay, so that's a factor then. So it's like so is that the reason why it's taking 5 seconds for ChatGPT to return?
Exactly. Yeah, that's exactly the reason why.
So then if I can come up with a less, so is there a way, like I don't know, like just tell me if it is like possible to like magically, these are all numbers eventually, like
Yes.
floating point numbers.
Yes.
Like I don't know, some genius mathematician can come up with a way to represent all these like giant numbers
Yeah.
in a very like a more efficient way to like
Yeah.
so smaller in size, but accurate representation of all these numbers.
Absolutely. That's one of the big areas of deep learning research right now, is more compact representations, because the amount of communication that's going on inside a modern neural network is very high, and biological systems like our brains somehow can achieve the same results with much greater energy efficiency and probably less communication. So how is the brain doing it? So some of the breakthroughs I'll share with you, when we're talking about the weights between the neurons, those were traditionally modeled as 32-bit floating point numbers, okay? But a few years ago, one of the breakthroughs that was made in Google Brain was to replace those with 16-bit floating point numbers, cutting the memory requirements in half, speeding up, doubling the speed of the neural networks, but without sacrificing any performance. So those kinds of compression schemes are being heavily researched today, and it's very relevant. There's even compression schemes that can reduce from 16-bit floating point numbers to 8-bit integers. Although that you suffer a little bit greater degradation. So there's a lot of research going on in that area. Also, the backpropagation algorithm we were talking about, that involves a lot of communication. Essentially, when the error signal is propagated back through the network to adjust the weights, it's hitting the entire network. Well, it works, but that's not probably what happens in a biological brain. So there's a lot of research going on to understand if there's more local methods. Local meanings here that I only touch some of the parameters in the network, not all of the parameters.
Okay.
And that has a lot of implications, for instance, to bring down the cost of distributed training of very large models.
Awesome.
Yeah.
So I'm not able to see the screen. Can you unlock the screen so that I
I'm
can
sorry.
see the questions?
Okay.
I'm sure there are
Give me one
multiple.
second.
Yeah.
Give me one second.
Yeah. Okay. So maybe we can even read from these. Okay. So it looks like the top question is, how will the job market change as AI technology becomes more prevalent, and what skills most valuable in the future?
Oh,
So
sorry.
the job market, the job question is the top question. Am I going to lose my job?
So I'll tell you a little bit about my history. I've always been a bit skeptical of, the established system. So I was heavy into gold investing in the early 2000s.
Really?
And then in the 2010, 11 timeframe, I was heavy into cryptocurrency, and it had to do with, I had an interest in cryptography, but at the same time, I was interested in alternative financial systems. So these are the kind of things that I could I felt there's a weakness in the system. There's a lot of manipulation, let's say, in monetary policy. So I was hedging my bets. Okay, now in the case of what's going on with AI right now, I can see that it's going to disrupt everything, but I don't know what to do to hedge my bets, because this is such a large scale change is going to happen. I have kids. My older daughter is going to be in college in 2 years from now. I don't know what advice to give her, to be honest. The scale of the transformation I think the society is going to undergo is going to be hard to fathom. And I think what we're entering into right now is what my previous boss at Google, Ray Kurzweil, used to call the technological singularity. The point at which AI systems exceed, let's say, the intelligence of an average human and potentially even begin to self-improve. And the idea of a singularity is it's a point in the future which there's so much change happening that it's very hard to predict what's going to happen beyond that. So interestingly, coding jobs, entry-level coding jobs are under threat. I don't think we programmers expected that. There was a joke that, our jobs as programmers are going to be done when we finish automating everyone else's job. Well, that might not be the case. We might be automated faster than that. So it's, I'm sorry, Talip, I'm not answering your question directly, but it's a hard one to answer. Yeah.
So we should maybe we should get into AI a little bit then, maybe just so that maybe would that be a hedge?
I think as programmers, it's helpful to know about AI, at least from the perspective as a tool.
Okay.
From a career perspective, it makes a lot of sense to understand how to leverage this tool, because I think it's in front of all of us now that this is an extremely powerful tool. Yeah.
Awesome. The second question was about the ethical implication of the AI. So I think like others are also talking about it, the founder of OpenAI, even Elon Musk. And what's your take?
As the capabilities of AI systems have rapidly increased, this is going to become an extremely important question, because from a business point of view, there's an increasing incentive to use these systems to directly make decisions. And then there's the question of whether or not, remember, you train a neural network, how? Through the loss function. Well, does the loss function, does it actually align with what we want in society? So for instance, a neural network that's trained to make decisions about whether to insure a particular home. Okay, there's very clear use cases for AI and deep learning in the insurance industry. But as soon as you start putting it in charge of those decisions, it can start to make decisions that maybe optimize the financial outcome of the company, but essentially it displays a lot of racial bias.
Oh no.
Or regional bias based on where someone's living. It won't insure you. So you're optimizing maybe the revenue of the company, but it's in an unacceptable way. So this is one of the big challenges actually with using AI for decision making. But there's a very strong incentive to do it from the business world as well. So
but isn't it also a little related to how the models are trained? That like right now you're using the internet data, which is like all over the place. The information is all over the place. Most of them are not correct or racist or whatever, right? Like it's all, there's so much bias on internet, and you're using internet as the data source. Does it make sense to then like come up with a data set to train the model in a very like unbiased, like clear, fact-based way?
I think from the perspective of the good of society, yes. But here's the reality. Google had a system like ChatGPT developed in 2019. Okay, that eventually turned into Lambda. I saw it with my own eyes. So they were sitting on very sophisticated technology. This knowledge of the biases that were built into it because of the training data, people at Google knew that. And that's why the senior management was concerned about releasing it into the market. But did the market reward Google for that decision, or did they punish Google for that decision?
Yeah,
I think it's pretty clear that Google got punished for that decision.
Yeah.
So the incentives are such right now that ethics and those things are falling to the wayside.
So they just like released ChatGPT and just apologize for the incorrect data.
Right.
Okay.
Exactly. Yeah.
Right. So another one is okay, you created a startup in this domain. Yeah, that's like, what's the rationale that there are already like big tech companies? Like, how could you break into?
Yeah, I think there's a lot of people who have left research in the past few years to start companies. And one of the big reasons is because the big companies aren't as willing to take risks. So for example, with Google, one of the reasons Google won't take risks is because Google is seen as authoritative. When they serve information.
When I say something, it must be correct.
Exactly. That's the expectation on Google. And this makes them conservative in terms of what they'll roll out. But a startup can take more risks. So that's one of the reasons. And then, of course, if you just look at the history of Silicon Valley, there's a long list of examples of startups taking on much larger companies and being successful in a variety of areas, not just in AI, ML, but you just look at, for instance, Zoom. The founder of Zoom came out of Cisco WebEx. You might ask, why try and create a competitor to WebEx when that's a multi-billion-dollar company? Didn't matter.
Yeah, and also you mentioned the cost is now much less. That
exactly.
Small startups can also like create impact.
Yes.
Awesome. Another one was where did it go? Oh yeah, this one. Yeah, like I'm a software developer. I didn't do any research. I don't have any AI research background. I didn't do master's or PhD. Do I still have a chance? Can I get into AI even though I don't have years of AI research experience?
Oh, so one of the beautiful things about AI is it's not a fossilized, it's a very young and creative field, and people have come into it from very different angles and perspectives and contributed. So the neural network is, for instance, behaving more like a physical system than an engineered system where, you know, the engineers understand all its properties. So many physicists have come in and provided useful analysis of neural networks as they train, for instance. Some of the big names in AI research, like for instance, now I could be wrong, but I believe that Noam Shazir, who's one of the authors of the Transformer paper, left college early from his undergraduate program and didn't complete that at Duke University. And there's many other examples. I don't believe Jacob Devlin, who's the author of BERT, had a PhD in the subject. I'm another example. There's examples all over. So absolutely, this field is like young. It's open. If that's your motivation, it will take some time and effort. I mean, I was in research for 8 years myself, but it's certainly doable.
I feel also like you can, you don't have to be the core like a model builder, designer, trainer. You can start with like using the APIs that are already like available to you, and then you create solutions on top of that, right? Like you can, so building a solution doesn't take much, and then you can also start like probably downloading those models and like playing with those models and see how they work. So that doesn't take any master degree. So you already said like data sets are also available.
Yeah,
a lot of them are already available. Like it's not like unreachable stuff.
That's right. So just to give you a couple of examples, the entire text of Wikipedia in 40 different languages is available and cleaned up in a data set called Wiki40b that you can download from Hugging Face. There's an even larger data set called the Pile, which is terabytes.
Funny name, Pile.
It's just a huge pile of text, and it's terabytes of data. It's often used, the Pile is often used for training these foundational language models that underlie systems like ChatGPT, and that's freely available too.
Okay, so another question is how AI chat will make money outside of that?
I mean, I think for those of us who have like, I now use ChatGPT multiple times a week to automate programming tasks, and I get it to write code for me that would have taken a few hours to write on my own. So I think it's clearly delivering a lot of economic value. They're only taking $20 a month from me for that. I think they could potentially charge more.
Deal.
It's a good deal.
Okay.
So I think it's clear already that AI chat is generating economic value. How you turn generating economic value into making money, I think, you know, shouldn't be maybe that hard to figure out. But there's a question that if it takes enough people out of work and automates enough jobs, then maybe the entire economic model of capitalism will eventually have to be rethought. So, yeah.
So the next one is a little, I love that question. So I had the same question. As the training completes, so weights are frozen, the model becomes prod ready.
Yes.
Then, so for example, for ChatGPT, is it possible that ChatGPT can learn from the conversations?
So the way that ChatGPT is actually kind of learning from the conversations that you're having, it's not updating the weights in the neural network. But what it does is it kind of keeps the entire history of the conversation around. And as it's responding to what you're saying to it right now, it's able to kind of look back into the conversation using this attention mechanism. So there's actually been attention was introduced in 2017. Attention scales up quadratically as the length of the sequence increases, at least the initial implementation of attention. So it was hard to create an attention mechanism that would go back beyond like 100 or 200 tokens. There's been intense research on improving the length of the attention that the neural network can pay. And right now with GPT-4, it's something like 50,000 tokens, I think.
32K.
32,000.
Is that the thing? Like, okay, how far I can go back?
Yeah.
Like, or what's my memory for this session, basically.
That's your memory, exactly. That's not the only way to build a memory into this. There's other ways as well, for instance, involving, vector databases to store information. There's a lot of different approaches here, but the answer to your question, I think, is that if you were then to like restart ChatGPT with a brand new conversation, could it reference things it learned from the other conversation? No.
Okay. So then it's still, the weights are still frozen. We're not learning or we're not auto-tuning stuff from the conversations.
Yeah, the way I think to think about it is right now you have ChatGPT is a massive model. And so you have one instance of it, it's stateless, and it's running for millions of users around the world. In the future, if you have a personal model, then that you can fine tune and keep updating. But then that does require a personal model. And right now we're not there hardware wise to be able to run those things.
Okay, what's the next one is what can be the biggest risks of this area?
So I think
what can go wrong?
So again, as these become more and more powerful, there's going to be more and more temptation to use them for completely automated decision making. And then that's where things can go wrong. Because it's very difficult to know that the objective of the neural network is actually aligned with your objective. So for example, just to take an extreme example, if you put a neural network in charge of operating a nuclear power plant, it might be performing well for a while, and then all of a sudden it hits this outlier condition that you never trained it on, and it does something crazy. How can you be sure that the system you're deploying isn't going to do that? And with a neural network, you can't really look into it and understand what it's doing. Everything is there encoded in the weights. That's why it's called black box machine learning. It's opaque. You don't know what's going on inside of it. So that's the big risk.
Is it like I read somewhere that like the ChatGPT kind of stuff is not really understanding things, but it's more predicting a potential response. So is that the case, do you think, or is it how do you see that?
So I think it's a bit of a false dichotomy. Actually, being able to predict is understanding. So for example, if I can predict the weather 3 days from now, I have some understanding of how weather systems work, essentially. And that's the idea that underlies ChatGPT as well. And I'll give you a few concrete examples. If you tell ChatGPT to imitate a Linux file system or Unix file system, and then you create directories and change directories and create files, you can ask it, give me the output of the ls command. And it's able to give you the correct listing of the files that you created and the directories you created. So at some point, you have to say that, no, it has some understanding of how Unix file systems work. So that ability to predict is tied to the understanding.
Okay, let me see. Okay, I would like to ask your opinion about privacy in AI, especially for ChatGPT.
Well, I think there's several concerns. I mean, OpenAI does train ChatGPT on your conversations. Generative models in particular have a problem with privacy because they can often regurgitate information they were trained on. So for instance, a particular individual's social security number or a credit card number can somehow, come out. There's an area of research in machine learning, which is how do you train neural networks on user interaction data in a way that doesn't end up memorizing these details and leaking them out in other conversations. So yes, there are concerns, and there's active research going on in this area.
Awesome. Let me see. What's the next one is okay. You mentioned the training models and comparing the results with the right answer to tune the models. How does the chat robots know what's the right answer to compare?
Okay, so
yeah.
So training a chatbot is a two-step process. You have the training of the foundational model. The foundational model is trained on a very simple task, which is prediction. It's given some sequence of words in a sentence, predict the next word in the sentence. And over time, doing better and better on this prediction task leads to increased understanding of language and how it works. Once you get to the end of that process, that's how you train the base model. What you're going to need to do next is actually train or fine-tune the neural network on an instruction following data set. So this is a data set of the style where you say, okay, list the 5 largest countries in the world by population, and then I'm expecting, number 1, China, number 2, India, et cetera, right? And you give it 50,000 or 100,000 of these examples, and then you get this ChatGPT-like behavior. So it's a two-phase training, and a lot of the work that's happening right now is around the collection of open source data sets that let you take a base large language model or foundational model and convert it into a chatbot. Because OpenAI has a lot of this data, but they're not releasing that data to the public. So the open in OpenAI is a bit of a misnomer.
Open, huh?
Yeah, it's not that open.
Okay.
It's not that open.
So one thing that I was thinking, like, okay, so you said like the capabilities of a model is not that predictable, so they can end up seeing some of the capabilities that you never anticipated.
Right.
Is it possible that, let's say, you train a model with, like, let's say, I don't know, 20 languages, but the Turkish is not one of them, and now you can have the conversation in all these 20 languages, but is it possible, even though it's not trained, that you can have a conversation in Turkish?
So, okay. I don't think I'm completely qualified to answer that. I know in the area of large language models, there have been a few examples where the fine-tuning data, for instance, was never presented in Turkish, but it was actually able to begin to carry out conversations in Turkish, for example. However, underneath in the base model, it had seen some amount of Turkish training data. So it was able to transfer the idea of carrying out a conversation to a language it had never carried out a conversation in. So that concept of how to carry out a
conversation is possible. So that's a learned thing.
Yeah.
But using the characteristics of the language, like, even though they never seen, they still can mimic that.
Yeah, so whether there's an example of a neural network that had never ever seen any Turkish in any form, but is still able to carry a conversation, I don't believe so, but I could be wrong. I mean,
okay,
things move so fast in this field. So,
all right. So how to protect AI from hackers? Cybersecurity is a major issue even today. Once AI has access to the internet to learn, it becomes prone to hacker attacks.
Yeah, there's all kinds of interesting attacks on large language models. You can put false information out on a website and be pretty sure that OpenAI is going to train the next version of ChatGPT on it, and in that way influence.
Or you have enough money to create enough content, right? Like crazy.
Yeah.
And then because it's very much like the in the blockchain thing. If you have more than 50% of the compute power, then you have full control over the network. So let's imagine that some guy, like, let's say Elon Musk, so it started generating tons of content on the internet. So just now.
Well, I believe that's going to happen very soon. And there's the good thing is, I think that there's also an easy solution to that, which is pretty soon you're not going to care about content that's not digitally signed by its creator. So I think all of that infrastructure from public key cryptography and all that will all be leveraged to sign content in the future. But there's other examples of. Let me give you one more example. So now the question becomes, so ChatGPT or GPT-4 is pretty good at writing code. And there's a GitHub, what's it called? Codex is also good at writing code. that code has been shown in many cases to contain flaws, security holes. So it's become more and more dependent on code generation by these systems. How do we know that it's generating correct code?
Correct code or
not code with
secure code.
Yeah, there could be a lot of backdoors in that,
Yeah.
right? So it's going to be a big issue.
Is it possible to detect if a text is generated by ChatGPT?
I think that existing scheme, yes, and those schemes look at the word distribution to understand. But I think it's going to be increasingly difficult to do that. It will be increasingly difficult. But people have built those programs today, and they look at the distribution of words. I've even met people who have spent enough time looking at the output that they themselves can actually detect whether it was generated directly, because today ChatGPT has a certain style of talking, and it's a little bit verbose, and so when you see it, you can kind of recognize it. But I think that that's very quickly not going to be the case as these systems get more powerful.
Awesome.
Yeah.
Thanks so much, Amin. I think we crossed 8 p.m. already. Betul, what do we do? Can we say back to you, Betul? We cannot hear you. I think.
Can you hear me now?
Yes, we can hear you.
Yeah, thank you so much, Amin and Talip. That was very informative, very engaging, and I hope everyone enjoyed the session as much as I did. So yeah, that was great. Thank you.
Thank you. Thank you.
Awesome.
There's a survey shared on the chat. Thanks everyone for joining, and please fill out the survey as well. Yeah, so yeah, this was it for today's session. Again, please fill out the survey, and we will have more sessions coming up in the coming weeks, and the next one will be with Monica O'Hara, who is the CTO of HackerRank on marketing and growth. Yeah, so this is all I have to say, and thanks again all for joining, and thanks Talip and Amin for this informative session.
It was fun. Thanks so much, guys. Bye.
Bye.
Take care.